Welcome to BS Final Year Capstone Project, titled Soil Moisture Estimation from Sentinel-1 Microwave Remote Sensing Data Using Optimization Methods. This project applies advanced optimization approaches to transform radar signals into soil moisture estimates. Learn more at www.capstoneprojectshub.com. Soil moisture is a key parameter for agriculture, hydrology, and climate studies. But direct field measurements are costly and limited in coverage. This is where satellite data becomes essential. The challenge is that while Sentinel-1 provides backscatter measurements, it does not directly give soil moisture values. We must transform radar signals into accurate soil moisture estimates using mathematics. Our input comes from Sentinel-1 Synthetic Aperture Radar in dual polarization mode. VV means vertical transmit and receive, while VH means vertical transmit and horizontal receive. In this project, we use both VV and VH backscatter as input features. The observation vector B comes from Sentinel-1 Saudi Riyals backscatter. Here, B1 represents the VV polarization at incidence angle theta, and B2 represents the VH polarization at the same angle. These values are obtained directly from the radar, independent of soil moisture X. The unknown vector X represents the soil moisture we want to estimate. Here, X1, X2 and X3 correspond to the volumetric water content at 3 different ground pixels. These values are not measured directly but must be retrieved from radar observations. Feature matrix A links radar backscatter to soil moisture. Each row is a radar observation like VV or VH, and each column is a soil moisture pixel. Its entries show how each pixel contributes to the radar signal, making it the key link between satellite data and soil moisture. Here is the problem set up as a linear system. Mathematically, it is written as B equals AX. Radar backscatter B is linked to soil moisture X through the feature matrix A. Let's consider the feature matrix A, the radar backscatter vector B, and the unknown soil moisture vector X. Our goal is to solve the system AX equals B, and estimate the soil moisture values X1, X2, and X3. Here we see the visualization of soil pixels, along with the soil moisture values computed using the least squares method. Here we see the visualization of soil pixels, along with the soil moisture values computed using the Tikhonov regularized method. Here is the interpretation and comparison of results. Pixel 1 indicates very high moisture, Pixel 2 moderate, and Pixel 3 dry. Least squares may exaggerate values, while Tikhonov provides more stable and reliable estimates. The L-curve shows how the solution norm and residual norm change with different regularization values. Small lambda overfits and becomes unstable, large lambda underfits, and the corner of the L gives the best balance between accuracy and stability. GCV selects lambda by minimizing a statistical criterion. Small values overfit, large ones underfit, and the minimum gives the best predictive balance. In our example, both methods point to lambda around 0.1 to 0.2, ensuring stable and realistic soil moisture estimates. And before we dive deeper, if you want the full project documentation, source code, and ready-to-use slides, make sure to visit CapstoneProjectsHub.com, your one-stop hub for capstone project success.